Welcome back to lecture 7, I think this is. Okay, we've been talking for the last couple of lectures about completeness and completions. So I've been belaboring this a little bit, and there's a reason for that, because I wanted to spend some time talking about some easy cases, because we're going to see some hard cases of completions coming up, and I think it's going to be important to have in mind what a completion is, first of all, and second, to understand why completions are important. And we haven't talked very much about that second thing, so let's maybe say some things about that. Okay, so there's not going to be a lot of math I'm going to write down here. I'm just going to say some stuff. And to think about why completions are important, maybe it's useful to make reference to a situation about a completion that you already know about and that we talked about last time, which is the completion of the rational numbers to the real numbers. Okay, so why is that an important thing to do? Well, from a certain point of view, it's not important. If you're a working scientist, let's say, especially nowadays, you're never going to encounter anything even remotely like a real number. You're going to be doing all of your modeling on a computer, and computers are only really capable of storing rational numbers. So from that point of view, a real number does not seem like a particularly worthwhile or necessary, I should say, thing to have. But despite the fact that you never, get your hands on one of these, at least not with your computer, real numbers are important, and the fact that they're complete is important. And why is that? Well, there's a few reasons. One of just from a point of view of constructing mathematical theories that model reality, completeness is absolutely essential. And the reason for that is limits. If you're going to use any mathematical theory that makes use of limits, then you need completion. Completeness. And the reason is very simple, is that if your space is not complete, you may be taking a limit which doesn't exist, and it exists just for the reason that your space isn't complete. It doesn't exist for some interesting reason, like like it doesn't converge in the completion. It's just your space is not big enough to contain the things that you should be converging to. So, for example, for rational numbers, it doesn't contain all the real numbers. So what mathematical theories do you use that take advantage of limits? Well, calculus. So the mathematical underpinnings of calculus absolutely depend on the completeness of the real numbers. Without that, the tools of calculus would, I don't know, maybe you could try to make sense of them somehow, but if you dug very deeply into your calculus that you tried to build without making use of real numbers, you'll find things go bad pretty quickly. So completeness is something that you want to have. And another reason to think about why completeness is important is very much connected to the first, which is taking limits, and that is Cauchy sequences. So why are Cauchy sequences important? Well, the reason a Cauchy sequence is important is that it gives you an example of a converging sequence without needing to know what the limit is. If all you can do to test the convergence of a sequence is to find its limit, you're not going to have a great deal of success. But if you can get away with checking just Cauchyness of your sequence, that's going to be much, much easier. If you just think about a sequence like some j goes from 1 to infinity, 1 over j squared. Okay, so that thing converges. I forget, I think it converges to like pi squared over 6 or something. I don't really remember. Doesn't matter. Without knowing the limit of that sequence, you're not going to have a great deal of luck finding out what that limit is, or even knowing that the sequence converges, unless you have at hand the notion of a Cauchy sequence and the confidence that when you encounter a Cauchy sequence, it converges. Right? So you can say that the sum j equals 1 to infinity, 1 over j squared converges, without having to worry about what the limit is. And that's a very helpful thing to do, because in all over mathematics, and we're not going to see it very often. We will see it sometimes, sort of instances where we run into sequences that are Cauchy sequence, and working in a complete space will allow us to talk about convergence. But we will not see that often, just because we're kind of not going to be scratching the surface and deeply enough to see some of these things. But underneath, not very far underneath, a lot of what we're going to be doing here lies completeness. So it's important to work with spaces that are complete. Okay. And that's important to have in mind, because, as I said, we're going to encounter some spaces where to define their completions takes a bit of work. Okay. Okay, so that's sort of wraps up our general discussion of completeness and completions. So we've been a few lectures away from the sort of central topics of what I'm supposed to be talking about, which is signals. Okay, so let's sort of wrap up one part of our discussion of signals, and that is discrete time signals. Because I have enough information at my disposal to be able to talk about that subject completely. All right, so let me do that. We're going to let T be a discrete time domain. All right. And I want to talk about various kinds of, or spaces of signals, f-valued signals, where, as always, f is either R or C. Okay, and I want to be able to talk about classes of discrete time signals. So what I'm going to do is just sort of write down the common classes of discrete time signals that we're going to talk about. Okay, so I'm just going to write down some definitions now. Okay, so first, let's just, because you can do it and it kind of has some meaning here, we have f to the t, which is this space, by our notation that f to the t means mappings from t into f. This is by definition the all signals with f-valued signals with time domain t. Okay, so for discrete time signals, this is a meaningful thing. For continuous time signals, we'll see this is really not a very meaningful thing because of the complicated structure of the time domain. But for discrete time signals, this is absolutely a sensible thing to talk about. Okay, so now I'm going to introduce some signals, and these are going to make reference to the sequence spaces that I've talked about. So maybe let's just recognize here that sequences come out as a special case of this. Okay, so if you consider the time domain just to be a set of positive integers, then the signals defined on the set of positive integers, those of course are just sequences, right? So just to make connection to the things that we've talked about already. Okay. Okay, apologies, I had logistical problems there. Okay, so we're talking about discrete time signals, and we had this space after the t, which is the set of all signals, and which in the case where t is the positive integers can be thought of as sequences. Okay, good. So now we want to talk about other classes of discrete time signals defined on the time domain t. Okay, and we're going to do this in analogy with our spaces of sequences. And the first space of sequences that we thought about apart from the space of all sequences was this one, remember? And this was sequences where the zero here meant that all but finitely many terms in the sequence were identically zero, okay? And so the notation I use for the time domain, the set of discrete time signals, which are analogous to this, the notation I use is this: little c sub fin for finite, t f. Okay, and here I'm going to be making use of the notation that I use for spaces of signals throughout the course. Okay, so there's going to be parentheses, and there's going to be a domain and a codomain separated by a semicolon. And then sitting out front is going to be some symbology that says something about the character of the signals that I'm talking about. And in here, fin, as I said, means finite. And so these are the signals which are non-zero except on a finite set. Okay, so let me, oops. Okay, so it's the set of signals, discrete time signals on the discrete time domain t, with the property that there exists a finite s in t, okay? And so, the font means it's a time domain. And so it's a time domain which sits inside t, okay? So, and it's discrete and finite. So finite, remember, as a time domain means it's bounded from above and below. And for discrete time domains, that's also the same thing as saying it's finite as a set, which isn't true in the continuous time case, but we'll get there. Okay, so C finite means that there's a finite set S such that if T is in T take away S, then F of T is equal to 0. Okay, so outside this finite set S, F is equal to 0. Okay, so this is exactly, of course, analogous to this guy. Okay, all right, so that's the first collection of signals that I can talk about. And so, we know that we might expect, based on what we did with sequences, that this space generally is not complete. And we'll exactly say when it is complete here in a second. Okay. And so then for sequences, the first sort of complete space of sequences we built was this one. And the analog for that in terms of signals defined, discrete time signals defined on the time domain t is little c0. Okay. All right. And so the idea here is clear. Okay, so what were these ones? These were sequences that converged to zero. So these are going to be signals that converge to zero. But what does converge to zero mean? Because the time domain could be, for example, unbounded from below but bounded from above, bounded from below but unbounded from above, or unbounded on either side. So you want to make a definition that sort of covers all of those cases. And so, saying that the limit goes to zero at infinity is kind of an awkward way of saying that. Here's a better way of saying that. Okay, so it signals on the time domain t such that for every epsilon positive, there exists a finite time domain S contained inside T, rather like in the situation above, such that if T is outside S, then the absolute value of f of t, or magnitude, is less than epsilon. Okay, so this just means that if you want to make the signal small, have value epsilon, you can always do that by considering sufficiently large times. Okay, so sufficiently large here means outside some finite s. Okay, so that's little c0. Then there's the little LP spaces, okay, and I'm just going to do them all at once. So I'm not going to do L1 and L2 separately. So there's a LP of F, okay, as a sequence space, okay, and here we're going to have little LP of TF, and this has the obvious definition. Okay, so it's the set of all discrete time signals on T, such that the p norm of f is finite. Okay, so this means that the sum of t's in T, f of t to the p is less than infinity. Okay. All right. So these are the and there's another space that I can introduce here, and so this is for of course, as always, as I said, for p going from 1 to infinity. But there is also the infinity case that you can talk about, and it's easy to do, so let's do it. So we didn't talk about this, but L infinity of f is simple enough. These are bounded sequences. Okay, and corresponding in terms of signals to the bounded sequences are going to be the bounded signals, which are of course L infinity. So let me sort of say carefully what that means. Okay. Right. So this just means they're bounded. Okay, so we're not going to talk very much about L infinity. We're mostly going to talk about little c0 and little L1 and little L2. Okay. But for to sort of fill things out a little bit and put a little bit more meat on the bone, there's some additional things we can talk about. Okay, now let's try to say some things about these spaces. Okay, so let's sort of first, we haven't put norms on these spaces yet, and so let's not do that exactly right yet. Let's talk about the algebraic structure of these spaces. And so again, algebraic structure means just dimension. Okay. So an easy fact, and I'll sketch how you do that, is that the dimension of f to the t is finite if and only if, and so this is actually true for all of the spaces. Okay, so let me say it all at once. Okay, dim C finite T F dim C0 T F dim double P T F, and here I'm going to allow P to go from 1 to infinity, including infinity, are finite if and only if T is finite. Okay, and remember, a discrete time domain being finite means it's finite, means bounded above and below, and for discrete time domains, that means it's finite as a set. Okay, all right. So to see this, so there's two parts, of course. One is that if the dimension, if T is finite, then all these dimensions are finite. Okay, so let's first look at that situation where T is finite. So suppose T is finite. Okay, so so first thing I notice here is that if T is finite, then we have, and I'm going to sketch this by drawing pictures and stuff. We have a basis for T as follows. Okay. All right, so we have a finite time domain. Okay, so that means that I have let's say a T1, and then a T2, and then a T3, and then a T4, and then a T5, and so on. Sorry, it's going to be way less confusing if I don't make those dots, but make them dashes. Like so. Okay, so I'm going to draw a basis. All right, so I'm going to draw the first couple terms of the basis. Okay, so T1, T2, T3, T4, T5, T1, T2, T3, T4, T5. And this is entirely analogous to when we looked at Fn as f to the 1n. Okay. And how did we define a basis there? Well, we had this set, and we're talking about mappings from this finite set into F, and then we considered the mappings, n of them. One took the entry 1 and returned the number 1, and then all the rest of the set 1 to n evaluated to 0. And then we defined another vector where it mapped 1 to 0, 2 to 1, and all the rest to 0. Okay, and so the idea when you translate that to this picture is that I have a 1 here, so this is going to be my first basis signal, and then zeros everywhere else. Okay, and it goes on, and I'm pretending it only has 5 points. Okay, the second one, F2, will have a 0 here, a 1 here, and then zeros everywhere else. Okay, and then F3 will have a 0 here, a 0 here, and a 1 here, and zeros everywhere else. Okay. And so you can see that this is exactly analogous to how we translated the standard basis for Fn into a basis for this set of mappings. Okay, so that's how you show finite dimensionality, is because there's only going to be finitely many of these Fs, like I define, like so. Okay. All right. So now let's so that shows that if T is finite, then that shows, for example, that F to the T is finite. However, if you take a look at all these definitions, okay, so C finite, okay, what's C finite? So C finite says that there's a finite set S, so that if you're outside S, then F of T is equal to 0. Well, if you take the finite set S to be T, in the case when T is finite, you can see then that this space is exactly this space, okay? And for similar reasons, this space is exactly this space, okay? And for the little LP spaces, okay, for a finite time domain, the sum is always finite because it's a finite sum of finite numbers, okay? And then L infinity is also equal to this space because a soup of a finite set of numbers is always finite. And so the point is that when the time domain is finite, all of these spaces are the same, okay? Also, F to the T equals C finite of T F equals C0 of T F equals LP of T F, and it's true for every P when the time domain is finite. Okay, so finally, this gives one direction of this fact that if the time domain is finite, all of these dimensions are also finite. Okay. Now let's look at the converse, okay? And so we need to show that if these dimensions are infinite, then the time domain is infinite, is kind of how that reads. And we're going to show the contrapositive, which is we're going to show that if the time domain is infinite, I'm not sure if I said that right, but anyway, what we're going to show is that if the time domain is infinite, then all of these dimensions must be infinite. And the way we're going to show that is we're going to say that if the time domain is infinite, we're going to construct a sequence of a countable number of linearly independent vectors, which are in all of those subspaces, or all of those spaces of signals, okay? So conversely, if T is, not finite, then for each T in T, okay, so and there's a countable number of such T's, right? Because the time domain is discrete and not finite. Okay, so it's infinite. So that means that it's countable. So for each T in T, define F sub T. Okay, and this is going to be a signal on the time domain T by, and it's going to be the obvious thing. It's going to be one of these things. Okay, but now it's going to be defined not a finite number of them, but a countable a countable and infinite number of them. Okay, so ft is going to be ft evaluated at some t prime is going to be 1 when t is equal to t prime and 0 otherwise. Okay. All right, so it's just one of these, right? So at t, it takes the value 1, and everywhere else, every other t prime, it takes the value 0. Okay, so one can easily show that the set ft, t in t, is linearly independent. Okay. And we did this before, basically. And so I'm just going to go back and hearken back to the notation that we used. Okay, so we talked about in the space fj, this collection of vectors f sub j. So this is exactly the same construction, right? J is just being replaced by t, and instead of j, I'm using t, right? And so you can go back there and see that the space is the set of vectors is linearly independent, and so therefore, by the exact same reasoning, so is that one. All right. Okay, so since t is infinite, this gives an infinite linearly independent subset Okay, now these FTs that I just defined, they are in all of the spaces, right? They're obviously signals on T, so they're in there. They have finite support, so they're in there. They go to 0 at infinity, so they're in there. Certainly they're in every LP, for the p less than infinity, you have this sum, but that sum will consist of only one term. So that sum is certainly finite, so they're in LP. And for p less than infinity, and they're also, of course, in L infinity, because a function that's non-zero at one point is necessarily bounded. Okay, and so this gives a linearly independent subset of all of the spaces in which I'm interested. Okay, so that's this simple claim about the algebraic structure of these spaces of discrete time signals. Okay, they're all finite dimensional if and only if the time domain is finite. Okay. All right, so that's the algebraic structure of these spaces. Now let's think about their kind of analytical structure, and to do that, we use norms. Okay. Okay. All right, so we're going to kind of look at this, we're going to look at this from the point of view of, we have these spaces, like so. What's the right norm to use on these spaces? Okay, well, let's start with this one. Okay, well, we only have at our disposal right now the p norms for p1, 2, excuse me, and less than infinity, and then we also have the infinity norm. Now, that does not define a norm on this space unless t is the time domain is finite, right? Because these signals can, possibly, grow to infinity at infinity, and so none of those norms will not be defined. Okay, so let me record that fact. If t is infinite, none of the p norms, and this is for all p's, are defined on ft. Okay, so we're going to talk about this situation significantly later on. Okay, but for now, it just doesn't work. Okay, and remember that when t is finite, okay, we're in this situation here where all of these things are the same, and so in fact we can use any of the norms. Okay, and if t is finite, any of the norms is well defined. On ft, okay, and indeed, on all of the other spaces, because all the other spaces are equal to f to the t, right? Okay, so the point is, when t is finite, doesn't matter which norm you use. Okay, and that just corresponds to the fact that in infinite dimensions, in finite dimensions, all the norms are equivalent in a sense that we talked about previously. Okay. All right, so really the interesting situation here that arises is when the time domain is infinite. Okay. Okay. So C0, okay, so these are the signals that die off to 0 at infinity. So they're all going to be bounded. And so the infinity norm makes sense on those. Okay. LP gets the P norm, of course. And that statement holds for every P. Okay. And then the remaining one is C finite. And C finite, because every signal in C finite has finite support, you can use any of the norms, in fact. Okay. All right, so those are the norms that so when I write down C0 and LP and C finite, these are the norms that I have in mind. Okay. All right. Okay, so completeness. If T is finite, all spaces. And again, because they're equal. Are complete. Okay, so again, the interesting thing only happens when T is infinite. Okay, so we have all of these spaces, right? F to the T doesn't, even if T is infinite, F to the T doesn't have any of the norms. So it doesn't make sense to talk about the, at least not the way we're living our life right now, to talk about the completeness of this space. But we can talk about the completeness of this space, or these ones. Okay, and so we know what the situation is going to be because of our work with sequences. So in the case of an infinite time domain, the situation is very, very closely analogous to the sequence case, right? So the sequence case, we had this as being C finite, this is being C0, and this is being LP, similarly for P equals infinity, okay? And what do we know was true in the sequence case? Well, in the sequence case, this was the completion of this in the infinity norm. And this was the completion of this in the P norm. This wasn't actually the completion of this in any norm. Okay. All right, so let me record those facts. Okay. If C is infinite, then C finite F is not complete. And its completion in the infinity norm is little c0, just like in the case of sequences. And its completion in the P norm. Now we're going to take P from 1 to infinity, not including infinity, is obviously little LP. Oops. Okay, so then again, this is entirely analogous to what I did with sequences. All right. L infinity is complete. But it's not the completion of C finite. with the infinity norm. Or any other norm as far as I'm aware. Okay. And the reason is that L infinity is too big. Okay. So what that means is that if I take, there are sequences in L infinity, let's say the sequence of ones. Okay. These are not going to be the limit in the infinity norm of Cauchy sequences in here. Okay. And it's rather the same as the situation I talked about last time with C not being the completion of the rationals because C was too big. It's exactly the same kind of situation. Okay. All right. So that covers completeness. Okay. So let's talk about inclusions between these spaces. Okay. So in other words, how are they related to one another? If indeed they are at all. Okay. So again, if T is finite, they're all the same. So that's dull. Okay. So assume that T is infinite. All right, so how are these things related? Well, so what are the spaces we're talking about? It's these ones. Okay. So certainly, this is the biggest one, right? It's the space of all signals, and this is the smallest one. Okay, of the ones I have listed here, right? Finite support means that it's always in little c0 and it's always in all of the LPs. Okay. All right. So ft is the largest, and C finite is the smallest. Okay, so what about ordering things in between? Okay, so let's maybe sort of cover L infinity first. So L infinity are the bounded sequence, bounded signals, and so certainly things in little c0 are bounded. They go to 0 at infinity, so that means they're less than 1 outside some finite set, so therefore bounded. L1 and L2, for example, will be in L infinity. And that's because the LP spaces are defined by a requirement like that, right? And so in order for this sum to be finite, it must necessarily be the case that the terms in the sum, which are these guys, go to 0 as t gets large. Okay, and so that means that the terms in this sequence, and the sequence here, I mean, to be defined by t, is bounded. Okay, and by exactly the same reasoning, the LPs are all contained in little c0 as well. Again, because as t gets large, these things have to get small. Okay, so we have so what I just said is that LP is contained in C0, is contained in L infinity. Okay. So the only thing remaining to decide is the relationship between the LP spaces with each other. Okay, so as P gets larger or smaller, do these things become related? All right. So let's think about this in the case of P equals 1 and 2, and then the general case follows by similar reasoning. Okay, so for a sequence to be in L1, it should be summable. Okay, now if it's summable, then its square will also be summable because the large terms in the sum with the components, with the terms in the function squared will get smaller when you square them if they're already small, right? So in other words, at infinity, when you square something, it only gets smaller. Okay, and so therefore, what you can conclude from that is that if you're in little l1, you're also in little l2. Okay, and the relationship holds for arbitrary p's. So we have that P of TF is contained in LQ of T and F for P greater than Q. Sorry, Q greater than or equal to P. Yes, that's right. Like that. Okay. Right. So again, for example, let me just double check to make sure I have this right. So this says that L1 is contained in L2, which is true. Okay, good. All right. So that indicates how these spaces of signals are arranged relative to each other. And the main point is that they're not the same. Okay, so you have some inclusion relations, and so what this shows you is that the norm, the character of the spaces depends on the norm that you're using. Okay, so we're using the infinity norm here and the P norms here. Okay, and you're changing the P norms here, and so the character of the spaces changes. Okay, so that is everything that I wanted to say about discrete time signals, and so next time we're going to begin talking about a rather harder subject, and that's continuous time signals. Okay, so we'll pick that up next time.